Hello, world. Good to see everybody. As Lizbeth mentioned in Slack, I am not in my usual location in Mountain View, California. Rather, today I am in my childhood home in Vienna, Virginia. This is my dad's office. It is nicer than my office in California. We are going to be going over the fourth project of term 2 today, PID control. We'll be working with the simulator and building a PID controller to drive the car around the track in the simulator. It's a fun project. It's a pretty short project. A big reason to do the project is simply to make sure you can get everything up and running with the simulator. Originally, this was going to be the very first project in term 2 that used the simulator. We've since changed that a little bit, so all of the projects connect to one version of the simulator or another, but this is still a pretty short and easy, or hopefully easy, we'll see, project that kind of sets you up for the model predictive controller project. I am doing this project in Windows today because I know a lot of students who work on Windows have had issues getting everything set up and connecting to the simulator. I am not super experienced with coding on Windows, so we'll see how this goes. And in fact, I think what you're going to see is a very Unix-like experience of coding on Windows. It will be what you would expect to see a Linux developer do on Windows. But hopefully we can prove that at least there is a way to connect to the simulator on Windows, and it's helpful to students who are working on Windows in terms of getting things up and running. So with that said, we'll dive in and we'll get started. I'm gonna, forgot I need to screen share. Screen share going. Actually, I should probably kill Slack just so we don't see any random messages. So this is the homepage of the project, the Car ND PID control project in GitHub. And you can see there are a bunch of dependencies for the project. The very first thing we're going to do, though, is just clone down the repo. Before we even get started, or before I got started on this live Hangout, I installed something that I won't show you here because it takes a little bit of time to download, but it's Bash for Windows. Now, this only works on Windows 10, so if you're not on Windows 10, it might make sense either to update or we have a Docker container and other solutions that work on older versions of Windows. But for Windows 10, this is a pretty interesting way to go about developing the project. Essentially, there's a way to install Linux or something Linux-like, very Linux-like, natively on Windows. And if you Google Bash for Windows, this is the installation guide for Bash on Windows. You have to step through a few settings and then get things running, but I found it pretty straightforward. And so what I have here on my Windows desktop actually is Bash on Windows. And so hopefully you can see me full screen here. And what I'm going to do is I'm just going to run git clone, and then I'm going to clone down the project repository. So I have the repo. That's what my directory looks like right now. I am in the home dsilver directory. This so far feels, very Linux-like, so I'm very comfortable with it. If you're not normally a Linux programmer, it might be a little bit less comfortable, but hopefully it's not too difficult to get going on. So I'm going to change into the project directory, and then I'm going to go back to the homepage for the project and look at the instructions. There are all these dependencies. That seems like a lot of stuff to install. So I'm just going to skip it and go to the build instructions. This seems easier. 4 steps. Clone the repo. I just did that. Make a build directory. So let's do that. Make dir build and cd into build. Easy. Next step. Compile cmake. And make. So we're in the build directory, so we'll run cmake on the directory one level above, and then we'll make. And cmake is not currently installed. Okay, so we do apt-get install cmake. All right, password. All sorts of things to add. All right, so this will take a little bit of time to download. I apologize for making you watch the download. I have practiced this before. We're not totally flying without a net here, but I thought it would be helpful to start from scratch, just so some of the folks who are having issues on Windows kind of get to see pretty much everything to go from 0 to up and running. If this is not helpful to you, then I apologize. You can either tune in about 5 minutes and see everything running, or you can come back and skip this part in the video that we'll post of this live stream. So here we go. Looks like there was some error there. Unable to fetch some archives. Maybe run apt-get update. Okay, so let's run sudo apt-get update. So here we go. Running some updates. All right, now that we updated, let's try installing CMake again. Installing. I feel like I should have some good jokes or maybe a funny story. Mainly what I have is a screaming 1-year-old in the other room. But he says hi and wishes that he were in the program too. So this will unpack CMake, and then I can tell you, because I've done this a few times now for practice, we're going to run into some issues coming up where we're going to have to install some additional dependencies, but it should be pretty straightforward. And then hopefully we'll be able to get the simulator up and running. So this is this might be new to you if you're mainly a Windows developer, and some of the instructions on the project homepage are a little more geared towards native Windows development without relying on Bash for Ubuntu. But my colleague Aaron Brown, who does do a lot of his development on Windows, has told me he has found that working with the simulator, both for himself and for a lot of students that he's talked with and helped troubleshoot, it's just worked much better and more cleanly on Bash for Windows. And so we'll probably put something up in the classroom that kind of walks through the steps I'm going through now, so students have a little bit easier time of doing the project on Windows. So, all right, so we installed CMake. So let's go all the way back to, this is the program we want to run. We want to run CMake on the directory above and then make. So let's see. The environment does not know where the compiler is. So we need to tell CMake where to find the compiler by setting either the environment variable CXX or the CMake cache entry, whatever. Let's see, do we have a compiler? Which G++? No G++, which GCC? No GCC. Let's install G++. Sudo apt-get install G++. So here we go. And again, apologies to those of you who are not super interested in seeing me set up a development environment. It seems like this would be helpful, but I realize for some folks, maybe it's not so helpful. Definitely feel free to come back and fast forward for this later. Let's get right to the coding part. Hopefully this is helpful to some folks getting things set up. Okay, so we installed G++. We'll run this again. Oops, we still don't really have the compiler, I don't think. Oh, it does have the compiler. All right. Let's see. Fatal error, uws.h. I think we have something like that up here. What did we skip? WebSockets. That UWS looks like WebSockets. And we say you can run either install-mac or install-ubuntu, or you can do it from source. Bash on Windows, this is more or less the Ubuntu logo. This seems pretty Ubuntu-like. So let's just go up a level to where I think install-ubuntu is. Yep. And let's run install-ubuntu and see what we get. So, yeah. No, installing. Remember, the whole goal is just to get UWebSockets installed. UWebSockets is actually how the simulator, which we still haven't actually downloaded yet, the simulator talks to the C++ code. We're still downloading libraries, but hopefully they'll get all set in a second. Right. Looks like we're building some stuff for WebSocket. Installing. Okay, let's see. So we installed WebSocket, and it looks like a bunch of other stuff. And let's see. Let's go back. Let's try and run CMake and make again. Oh, we're in the wrong directory. Oh my goodness, miracle of miracles, everything built. All right, so we should have this executable called PID, I believe, but let's go back to the instructions. Instructions say compile, CMake, make, run PID. All right, let's try and run PID, see what happens. Okay, so PID, our PID executable is listening. Who knows what it's doing because we haven't written any code, but let's download the simulator and see what happens. So let's see, somewhere in here, there's something about where to get the simulator. Let's see, oh, simulator. You can download these from the project intro page in the classroom. Click on this, see, we don't go to the classroom, but we do go to this handy page where we have a bunch of Term 2 simulator links. We'll download the Term 2 simulator. It looks like that's gonna take another 10 seconds or so. I will show the folder where it is. Let's see. All right, let's extract the simulator here. Extract. Let's see. Term 2 sim. All right, let's play the simulator. So the Term 2 simulator has a bunch of different projects, actually. So as opposed to Term 1, where it was just kind of one simulator with a couple tracks, Term 2, the simulator, you basically have to select which project you want to do. So this is the PID controller project. So we'll select into that. And remember, we've got this PID control file running in the terminal. So let's see what happens. And the car drives. It's great. It's a win, right? It's not really steering, not steering at all. Off the road it goes. Oh well, at least we got something working. Thank God for small victories. So let's see, what do we do now? We're in this build folder. I'm actually going to take advantage of a program called Tmux now, which is a program that allows me to divide the terminal in two, basically. Makes it a little bit easier to run do multiple terminal things at once. You don't have to use Tmux. If you prefer to use just a normal editor, that would be fine. Here we go, we'll run Tmux. We're in the build directory still. I'm gonna divide the terminal in half. So on the left-hand side here, we're in the build folder, and on the right-hand side, we will go into the source folder, and let's look at what source files we have. So we've got some sort of a JSON file, we've got a main file, and then a PID class file and a header file. So let's look at the main file. Actually, let's go back and read the instructions. So let's go back to the project homepage. We have these build instructions and hints. You don't have to follow this directory structure, but if you do, your work will span all of the CPP files here. Doesn't say anything about the H files. Keep an eye out for to-dos. Okay. So we're in the terminal. We're in main.cpp. Let's search for some to-dos. To do, initialize the PID variable. So let's see. I don't really know what initialize means, maybe. So let's look at the PID header file and see if we see anything about. Oops, sorry. So here's the header file. This covers what the PID class is. Let's see, there are some doubles that look like they're the PID error terms. There are some coefficients. Again, it looks like PID. There's a constructor, a destructor. There's this init function. There's an update error function and a total error function. So init, I guess, involves passing 3 coefficients, and then presumably we should build out init so it sets the arguments passed into the member variables. So let's go back and do that. Let's see. So where was that to do? Here's that to do. So we're going to call PID.init, and we'll pass in init kp, init ki, and init kd. I guess we need to set those variables. We'll set init kp. We'll just set them all to 0 to start. Init doubles, because that's what member variables of the PID class are. Double init kd. Let's see. So got that init function. Oops, sorry. I just asked Elizabeth if the audio and everything was working. She's saying it is. So let's see. So we've initialized. Oh, please don't. Probably pulled Slack. Slack. I love Slack. Just didn't want it popping up in the middle of all of this. Let's see. Is there another to do? I think there is. To do, initialize the PID variable. To do, calculate the steering value here. Remember, the steering value is -1 to 1. Note, feel free to play around with the throttle and speed. Maybe use another PID controller. Man, that sounds like a lot of work. Okay. So let's see. Calculate the steering value. So we have this double up here, its steer value, and presumably we want to set it to something. So let's say we set it to 0, just for starters. Let's go back and just see if we can make everything that we haven't regressed, that we can still get the simulator to drive, at least drive straight. So let's see. We're making make process here is a little bit slow. I apologize. Bear with me. Steer was not declared in this scope. Oh, see, there you go. Looks like I left out an underscore character. All right. So let's see, after we get everything running, assuming that we haven't broken anything, we'll probably set the steer value to the standard PID control formula. And then the name of the game will be adjusting those coefficients, the PID coefficients, to try and get the car to actually drive better. So let's see, let's just make sure that we're still in the same place we were a few minutes ago, that the car drives, at least drives straight off the road. All right, the car is driving and it looks like we're getting all these CTE values in the terminal over here, but the steering value is always 0. That's what we told the steering value to be, so that's fine. Okay, so far so good. So let's come back. Let's figure out how do we want to set the steer value here. So you might remember how PID controllers work from class. If not, there's always Wikipedia. So if we look at, we don't want to buy a PID controller. We want Wikipedia. If we look at the Wikipedia entry for PID controllers, basically we have our output here, control variable U, is KI, KP, KI, and KD, those look familiar, times, this is the proportional error term, this is the integral error term, and that's the derivative error term. So if we come back into our bash terminal, basically we want KP times P error plus KI times I error plus KD times D error, except that I think we're going to get a compile error here. Let's see. I think we're going to get a compile error. We should get a compile error. Come on, compile error. I hope this would happen faster. There we go. There's the compiler. So we don't, like, these are all variables we haven't set, KP, KI. So you know what, actually, instead of coding this up ourselves, maybe we should just rely on the PID class. So the PID class has this function called total error, which is we could use more or less to set the steering value. If we did that, then what we probably want to do is go into the PID class. PID class looks pretty simple. We've got this init function and this total error function. So let's see, for the total error function, maybe here we want to put what we were typing in main before. So KP times P error plus KI times I error plus KD times D error. And that should be fine, except we never really initialize or set any of these variables. So let's do that now. Let's start with setting the member KP variable to be the argument passed into the init function. And this will be the same for this will be the same for I and D as well. So here we're setting the coefficient of the member variable to whatever the arguments being passed in are, and we'll initialize P error to be 0 and ditto with the I and the D error. So all right, so now that should work. Let's make sure we can still steer the car straight off the road. There we go. Come on, come on, come on. Come on. So one of the things we're observing is making this seems a little slow, particularly given how lightweight all of this code is. So we might want to find a way around that in a little bit. But for now, let's just make sure we can still drive straight off the road. Let's see. Hello, Oliver. So yes, we can still drive straight off the road. Okay. So what do we want to do so we do something more interesting than drive straight off the road? Well, that probably lives in this update error function. And so Well, it's a combination of the update error function, and if you remember in main, we're passing in zeros as all of these coefficients. So maybe actually we should go back to main for a moment and pass in something more interesting than zero to the coefficients. So we're going to initialize Kp, Ki, and Kd as 0. If you remember from how a PID controller works, the proportional term deals with how far you are off of where you want to be, off of the center of the road, basically, and how hard you want to steer back to the center of the road. So basically, if we're off to the right, we want to steer left, and we're off to the left, we want to steer right. So this proportional term is going to be negative. It's hard to know exactly what value negative we want to set it, but let's start with -1 because that seems like a nice round number, and we know the steering is between -1 and 1. So it seems like it's more or less the right order of magnitude. The integral term has to do with if we're consistently like pulling to the left or the right, like if the wheels are a little bit out of alignment. For the simulator, until we prove otherwise, I think we can figure the wheels are in alignment. And the differential term or the derivative term is related to trying not to oscillate so hard around that center line. So we're basically trying not to turn so hard. We'll leave the derivative term set to 0 for now. We might want to adjust that later. But for now, let's just see if we can get the vehicle turning back toward the center of the road. So we set the Kp term to -1. So the car should turn back to the center of the road. But in order for that to have any meaning, we have to go back to our PID function, and let's look at the update error. Sorry, the PID class, and let's look at the update error function. So we've got this variable that's being passed in, the cross-track error, and as I mentioned just a second ago, the P error basically is our cross-track error. Not basically, it is our cross-track error. It's how far are we off of the center of the road or where we want to be. The I error is the cumulative sum of all of our cross-track errors. So if we're consistently off to the right, then the I error just kind of piles up as being this off to the right error, and the same as if we're off to the left. And if we're kind of a mix of off to the left and off to the right, then the I error should hover pretty much around 0. And shouldn't be much of a big deal. And then the D error is how much we changed since our last cross-track error. So what we'd like is something like CTE minus previous CTE. The problem, of course, is that we don't have a previous CTE. That's not a variable that we're tracking. We could add it as a variable to track, but one of the things you might notice, actually, is we're keeping track of our CTE variable here. We change it at the top of the function. But at the time we enter this function, like before we hit this very first line, the CTE error or the P error variable that we are keeping track of, that is equal to our previous CTE. We set the CTE, then we go through the function, and then the next time we come to the function, the P error is already set as our previous CTE, and then we want to update it. So the trick we can pull actually is if we just delete this line and we paste it up top, we can, instead of saying CTE minus previous CTE, we can just say CTE minus P error, since the P error is our previous CTE, until we update it. So now instead of a PID controller, I guess you could say we have a DPI controller. Just flip the order of the terms around, it doesn't matter, but I think that should work. So there's one last thing I think we need to do before this is all going to tie together. Maybe multiple last things, maybe I'm forgetting things. But we're not actually calling this update error function anywhere. So if we never actually update the error, it's great that we have an update error function, but it's not going to help unless we actually call it. So here, before we calculate the steering value, we're going to want to call our update error function with the CTE value. So let's see. So now we've got this PID function with a -1. For our proportional coefficient. We're not dealing with the integral and derivative parts of the PID controller yet. We're updating the error, and then we're calculating a steering value using our total error formula. Let's go back and let's make this. Here we go. So now the goal is going to be to run the simulator and see if the simulator actually steers at all. Hopefully it will steer kind of always opposite the direction, or always back to the center line, basically. So if it goes off to the right, it should steer pretty hard back to the left. If it steers too hard, we might have to increase the size or decrease the size of our, or decrease the absolute value of our P coefficient. And if it doesn't steer hard enough, we might have to increase the absolute value. But let's, oops. We were already in the simulator. Let's go back and restart the simulator. All right, so there's some steering. That seems good. All right, and it even seems to be steering around the center line. So far, so good. Oh, this even looks like pretty reasonable. The car's going, the car's going, the car's going. Oop, now this looks like we're getting out of control. Whoop, there we go. We left the road. Okay, well, still, we got something. We got a car that was steering and kind of moving down the road. So that was pretty good. What we can do to deal with the fact that the car seems to be kind of oversteering to the right and then overshooting to the left is basically dial off our proportional term. So take that proportional term down closer to 0. We can also add something to our derivative term, add a negative value so that we basically try and minimize the amount of change. So if if we're steering left and all of a sudden we want to steer really hard right, we add a term that basically diminishes the controller's urge to steer back really hard right, just kind of moderates things a little bit. So we'll just set the derivative term to 0.5 since we dialed off the P term to 0.5. Again, it's hard to know exactly what even the right order of magnitude is here, but let's just kind of experiment and see what we get. So we'll make the build again, and man, the build is taking a really long time to make. So we might, if we have to keep fiddling with the coefficients, want to re-architect main.cpp just very lightly so that we can play around with different coefficients without having to recompile the entire build every time just to work with new coefficients. So we'll think about that in a second. But for now, let's make sure we've got our simulator. Yep, our simulator's in a neutral state, and let's run it. So let's see, driving down the road. Again, it's kind of weaving a little bit, but it looks okay. It's all right. Drive. Oop, things are getting kind of ugly again. So getting ugly. Ooh, are we going to make it to the turn? Maybe. All right, we made it to the first turn. That's progress. It's not very pretty, and we're about to lose the road, but so far those curbs, oh, we lost the road. Okay. All right, so better. So I mentioned earlier we might want to add something to main.cpp so that we can change coefficients without having to recompile everything. So we can, the standard way to think about this is to add a couple of arguments to main. There's argc, and then there's argv. Argc is a count of how many arguments are getting passed in from the command line. Argv is a vector of each of those arguments, strings. Since the strings are coming in, we're going to need to convert the strings to floats or to doubles. We will say that the first argument, actually it's the second argument because the 0th argument is the name of the executable, so PID in this case. So the next argument, argv1, is the first coefficient we would pass in, and then argv2 and 3 are the next coefficients. So let's try and make this. Make, and hopefully when this is done, we no longer have to build the solution at all anymore. We can just kind of fiddle with coefficients and never have to build the solution, and that'll be easy peasy. But it does have to build once. It's not building very quickly. Okay. So for safety's sake, let's just try and redo what we had done before, but with arguments being passed in from the command line. So those are the same coefficients we were using before, and let's just make sure that the vehicle performs more or less as well or similarly to how it performed before. Should get somewhere around that very first turn and then error. So here we go. Yeah, that's about right. It's getting to the very first turn, and now it's going to lose the back. So we'll just kill it. All right. So from here on out, it's basically parameter tuning. You know, I might just keep kind of backing off the proportional term and maybe increasing that derivative term or the absolute value of each of those terms, decrease the absolute value of the proportional term and increase the absolute value of the derivative term, and just kind of see where things go. And if it does start to seem like, man, the car is always pulling to the right or the left, then maybe adjust the integral term a little bit. But I believe the car should always be more or less well aligned, and that integral term shouldn't be too critical. Let's see, you can see the car is even doing a little better here with these new coefficients. It's still, you know, leaving a little bit. I wouldn't want to actually be riding in that car. It makes me a little seasick just watching it. But it's doing all right. You can kind of imagine how we might get from here to a car that performs a little better. So it's a bit of parameter tuning, and then you can even start playing with the speed and see how fast you can get the car to drive. I've seen some students on Slack saying they got the car up to maybe 100 miles an hour, which is pretty impressive. My goodness, the car really is staying on the road kind of barely with the help of the bumper curves. You might wonder, like, you know, why are we tuning the parameters by hand, given that, you know, Sebastian showed us how to use Twiddle to tune the parameters, and that is a very good question. Twiddle is a great algorithm. I think the formal name of Twiddle is gradient descent. That's what academics would call it. And it's a better way of tuning parameters than just kind of the guess and check method that we've been using here and that we've used in some other projects. One issue with Twiddle, man, the car really did kind of sort of make it all the way around. One issue with Twiddle is that it needs to be able to adjust the parameters and then calculate a cost value so that after adjusting the parameters, it can figure out, you know, am I doing better or worse than I was doing before? And the ideal way you might want to do this is to be able to run the simulator in a kind of headless mode where you didn't have to wait for the car to actually take like a minute to drive all the way around the track to figure out like what was your total CTE after you adjusted the parameters. You'd want to be able to run it like instantaneously and then adjust those parameters very quickly. We don't have a headless mode for the simulator. Maybe somebody will submit a pull request or maybe we'll just get that done ourselves. I have seen some students get around that issue by doing things like adjusting the parameters for like 1/10 of a second and seeing how the car does, and then kind of adjusting the parameters as the car goes around the track, trying to measure where you get the lowest CTE, and that's one kind of interesting algorithmic way to choose it, or to choose parameters. It gets at one of the difficulties with parameter optimization, which is there are some pretty good parameter optimization algorithms out there in the world if you can calculate your cost function very quickly. But when you're dealing with cars and robots and such, sometimes you have a pretty high fidelity simulator. Like if you're just working with camera images, you can run camera images through your computer, and you can calculate your cost functions very quickly and use something like Twiddle really well. Other times you actually like need to be in the vehicle, and tuning the parameters is a much more time-consuming process. So that points to some of the difficulties with parameter tuning and also the value of high-fidelity simulators because they allow you to do so much more efficient parameter tuning than you can do if you actually have to be dealing with the real world. So that's kind of a quick demo of PID. I know we spent a lot of time on setup. Hopefully that was useful to folks who are having trouble getting things set up. We'll try and put some of this in the classroom because I know that's been a pain point for folks. I also know this is a very Linux type way of coding on Windows. We should do something that's a little more Windows native, and we'll try and get that out to you guys soon as well. We have a Docker container that you can use if you're comfortable with Docker, and we'll try and make some of the other Windows setup procedures a little bit clearer. Hopefully that was helpful. I think I'll shut down the simulator now before I get sick, and let me flip over to the YouTube channel on my other computer here. Actually, on my original computer, I will. I'll turn off screen sharing, and let's see. We have a few people watching. 11 people. Hello world. Cool. Let's see. Let's see. We got a couple questions from Rana. With the motion models and Markov models. With motion. Sorry. I'm looking at one computer from another computer, so it looks like I'm off to the side of the screen. With the motion models and Markov models portion related to PID control project or useful to create the controller. So motion models are super helpful, well, basically required for model predictive control. So model predictive control is the next project, and that's where we actually model how does the vehicle move through the world, and we try and predict how the vehicle will move if we set the steering angle in some way and set the speed in some way. And then we're constantly kind of updating our steering angle and speed based on where the vehicle is and how we think it should move next. PID control is a totally different type of controller. It is I find in many ways less intuitive, because I find model predictive control to be intuitively very clear, but model predictive control is mathematically much more complicated because you have to build out these models and optimize. You use a solver, an optimization engine to predict how your steering and throttle control inputs will affect the model over time, and then adjust. Whereas PID control, you basically just set some coefficients and let it run and see how it does. So I find PID control at the conceptual level to be a little bit less easy to grasp, but from a coding level, as you saw, it's not very many lines of code, whereas model predictive control is conceptually, I find a little more intuitive, but mathematically and engineering-wise a little more complex to implement. Let's see. I'm having a hard time thinking of all the material are related or not, separate modules. Yeah, so maybe we didn't make it totally clear, particularly if you've gone through the model predictive control lessons yet, why there are two controllers, a PID controller and a model predictive controller. And the reality actually is that there are many, many controllers in the world. I don't know, thousands, hundreds of thousands, maybe millions of controllers that have been written by academics, engineers, to do very specific things. By far the most popular controller is the PID controller because it is so simple to implement, as you just saw. Model predictive control is also popular because it is intuitive and it's pretty high fidelity. But there are lots of other controllers too. And the trick here is really just using the right controller for the job. So for something kind of quick and dirty, that doesn't require a ton of maintenance and isn't worth a lot of engineering effort, then a quick and dirty PID controller can be really great. And the nice thing about the PID controller is it doesn't take a lot of computational resources. So when you get to model predictive control, you'll see that model predictive control requires a solver to optimize or to predict what's your motion model going to do, and then how to update the control inputs to optimize that motion model. And that's pretty high intense computation. And if you're in a limited computation embedded environment, like on a self-driving car or in mini robots, you might not want to pay the computational price of a model predictive controller. And so there might be times when you just want to use a PID controller. There are other types of controllers, linear quadratic regulators. I did one class at one point where we used something called a shape-up controller. most of these other controllers tend to be a little more obscure. There are various trade-offs they have or situations in which they're particularly useful or not useful. But a PID controller and a model predictive controller are two kind of core controllers that cover the vast majority of controllers that are used in actual applications. And good for you to know, PID being kind of quick and dirty and simple, and model predictive control being much more complex and accurate. I hope that was a helpful explanation of how these modules tie together. And yeah, the motion model stuff, some of which we covered in localization, will come back into play for model predictive control, but not so much for PID control. P.S. Aravind asks, what is the maximum speed we could expect in a PID controller project? I actually have not tried to push this to its limits. I've seen some students in Slack talk about getting the simulator up to like 100 miles an hour maybe, but I can't remember if that was model predictive control or PID. My guess is it's probably model predictive control. As I mentioned earlier, model predictive control is higher, is more computationally intense, but more accurate, also high accuracy. And so you can probably go a little faster and still stay on the track using model predictive control. But I haven't pushed the PID controller to its limits, so I actually don't know. Be interesting to ask in the PID controller channel on Slack, but what the fastest people have pushed it to is, or look on the forum, see if that's been discussed. I think that's all the questions for now. Not a ton of people tuned in, maybe because everyone's already worked through this project, or maybe because I'm just a little boring. But I appreciate you guys watching. And if there are any other questions, post them in Slack. If there's any feedback, please send it to us in the feedback channel in Slack. It's really helpful for us. It's how we know about things like that students are maybe having issues with getting everything set up in Windows, and it helps us to know where to focus our efforts to make the experience better for students and help everyone learn a little better. Thanks for watching. I think that's all. If any more questions come up in the live chat, I'll try and answer them there for the next few minutes. Take care. Bye-bye.